Howdy. So what have we learned? We've learned that the change in Gibbs free energy is directly related to the change in entropy of the universe. Now, if you remember, the second law of thermodynamics says that if a process would increase the entropy of the universe, then it's a spontaneous process, meaning that it will occur without any outside intervention. And so if delta S universe is positive, because that negative sign, that means delta G is negative. And so we can also use delta G to determine if a process is spontaneous or non-spontaneous. We've seen that the Gibbs free energy can also be calculated from delta H and delta S of the system. Now, please remember, if you do not see a subscript on delta H or delta S, that means it is for the system. And also, please don't get confused. Here we have delta G equals minus T delta S of the universe. And here we have delta G equals delta H minus T delta S of the system. Now, if we assume that delta H and delta S are temperature independent, then we see that delta G depends on temperature explicitly. Now, this video is on transition temperatures. By assuming that the change in enthalpy and change in entropy for a reaction of the system is temperature independent, we can actually calculate at what temperature the reaction will go from being spontaneous to non-spontaneous. Now, remember, if delta H and delta S of the system have the same sign, then the spontaneity of the reaction will depend on temperature. Now, this means that we can actually calculate transition temperatures when a reaction goes from being spontaneous to non-spontaneous, such as boiling points and melting points. After watching this video, you should be able to determine if a reaction is always spontaneous, never spontaneous, or whether or not the spontaneity depends on temperature. And if the spontaneity depends on temperature, you should be able to calculate at what temperature the reaction goes from being spontaneous to non-spontaneous. And so this graph will assume that represents 4 different reactions. So the first row is one reaction, second row is another reaction, a third reaction, and then a fourth reaction. And so we're starting with the delta H and delta S of the system for these 4 reactions. And so the R stands for reaction. That also means system. Now, given our delta H, we can calculate delta S of the surroundings. And so remember, delta S of surroundings is equal to minus delta H over T. Remember that because we're defining the system as a closed system, and the only thing that's transferred between system and surroundings is heat and work. And so if we neglect work, the only thing that's going to change the surroundings is heat. And so if delta H is positive, that means heat is going from the surroundings to the system, and so the surroundings would be losing entropy. And so if we plug in our delta H over T, put a negative sign there, we get for that first reaction, 300 divided by, we're assuming 300 Kelvin, 300, and there's a minus sign. Now, typically entropy is joules per mole Kelvin, and enthalpy is kilojoules per mole Kelvin. And so because of the change in sign, because the change in units is why we have minus 1,000 instead of 1. And so for that first reaction, we see that it is endothermic, which means that delta S surroundings is negative. The second reaction is exothermic, meaning heat's going from systems to surroundings, and so the entropy for the surroundings is positive. Now, for delta S of the universe, all we have to do is add up the system plus the surroundings. And so 100 minus 1,000 gives minus 900. And so right away we can see that the second reaction here should be spontaneous at 300 Kelvin, and then the last one should also be spontaneous at 300 Kelvin. Now, to calculate delta G, we could either do delta H minus T delta S, or we could just do minus T delta S of the universe, and we should get consistent results. So we could use either of these two equations, and we should get the same answer. And again, because we have minus T delta S universe, so when delta S universe is positive, that means delta G is negative. And so you can think about if a reaction is spontaneous by either looking at delta S universe or by looking at delta G. So if delta S universe is positive, reaction is spontaneous. If delta G is negative, the reaction is going to be spontaneous. And so we can ask some questions about our table. So which does the sign of delta G depend on temperature? And so the easiest way of remembering is just if delta H and delta S have the same sign, then whether or not the reaction is spontaneous will depend on temperature. And so for the first one and the fourth one, delta H and delta S have the same sign, and so we're looking at the system. And so whether or not the reaction is spontaneous will depend on temperature. Which reactions are spontaneous at 300 Kelvin? And so again, that would correspond to delta S universe positive or delta G negative. And so that would give us the second and the fourth reaction. Which is spontaneous at all temperatures, assuming delta H and delta S are temperature independent. And so if we look at this equation down here, it's my favorite one, or one of my favorite ones. And so for spontaneous, delta G has to be negative, and so that means delta H has to be negative. And so that would be the second or the fourth row. Now, for this term here, you got that negative sign, and so delta S system would have to be positive. So delta H negative and delta S positive means that reaction should be spontaneous over all temperatures, assuming delta H and delta S do not change with temperature. Which is non-spontaneous at all temperatures. And so for non-spontaneous, that means delta G is positive, which would mean delta H is positive. So either the first or the third. And so this term has to be positive, and so delta S would have to be negative. And so that would mean the third row should always be non-spontaneous. And so there's only 4 possibilities. Always spontaneous, always non-spontaneous, spontaneous at high temperatures, non-spontaneous at low temperatures, spontaneous at low temperatures, non-spontaneous at high temperatures. And so again, if delta H and delta S have the same sign, whether or not the reaction is spontaneous or non-spontaneous depends on temperature. It's also kind of interesting if you look at this equation down here, what it shows you is that this term, the second term, becomes more important at high temperatures, and so entropy is more important at high temperatures, and enthalpy is more important at low temperatures. And so if we assume that delta H and delta S have the same sign, then there will be a transition temperature. Now the transition occurs when delta G equals 0. Remember, delta G equals 0 corresponds to a reversible reaction. It means delta S universe is 0. And so if we set delta G equal to 0, and then if we add T delta S to both sides, we get this. Now if we divide both sides by delta S, we get the transition temperature, the temperature at which the reaction goes from being spontaneous to non-spontaneous. Now, one thing you'd have to watch out for is make sure that you're using the same units for energy for your delta H and delta S. Remember, enthalpy is typically kilojoules per mole, and entropy is typically joules per mole Kelvin. And so at what temperature does the following reaction go from being spontaneous to non-spontaneous? And so we have 300 kilojoules per mole. Now, entropy typically joules per mole Kelvin. And so if we move the decimal point over 3, that gives us kilojoules per mole Kelvin. And so the kilojoules will cancel, the moles will cancel. 1 over Kelvin gives us a Kelvin. And so if delta H and delta S are temperature independent, then at 3000 Kelvin, this reaction will go from being spontaneous to non-spontaneous. That would be its transition temperature. Also notice from this equation that you only get a reasonable value if delta H and delta S have the same sign. So we said that reactions depend, the spontaneity reaction depends on temperature only if delta H and delta S have the same sign. This will only give you a positive number if delta H and delta S have the same sign. And because temperature is in Kelvin, it has to be a positive number. And so if we ask, what are the values at 3000 Kelvin? And so again, at the transition, delta S universe is equal to 0, which means delta S surroundings equals the negative delta S of the system, and delta G would be equal to 0. And so this is at 3000 Kelvin, because at the transition temperature, the reaction is reversible. So is the following reaction spontaneous or non-spontaneous? So we have nitrogen plus hydrogen going to ammonia, and we're given the delta H and delta S values. And so if we want to know if it's spontaneous, we have to know the delta G values. Also notice that because delta H and delta S have the same sign, whether or not the reaction is spontaneous or non-spontaneous will depend on temperature. So we could also ask, at what temperature will the reaction go from being spontaneous to non-spontaneous? And so again, if we take our equation for transition temperature, delta H over delta S, and in this case, our delta S is already in kilojoules per Kelvin, and delta H is kilojoules. They should also be per mole, and so we have minus 92.22 over minus 0.1989, and we get 463.7 Kelvin, which equals to 190.5 degrees Celsius. Remember to go from Kelvin to Celsius, you minus 293. And then if we look at this equation, so they're both negative. And so delta G equals delta H minus T delta S. And so this one's negative. This one is going to be positive. And so at low temperatures, this reaction will be spontaneous. Remember, a negative delta S will correspond to a non-spontaneous process. At low temperatures, this one is more important. And so at low temperatures, the reverse reaction is spontaneous. At high temperatures, your delta H is more important. And so sorry, did I get that wrong? So this is more important at high temperatures. And so at high temperatures, the reverse reaction is more, it's going to be spontaneous. And so at low temperatures, this one's more important. And so at low temperatures, the reaction is spontaneous. And so again, only 4 possibilities: always spontaneous, never spontaneous, spontaneous at high temperature, spontaneous at low temperature. So we can look at another reaction. Sometimes it's interesting, what can you tell about the reaction just by looking at it without doing any calculations? And so we're going from 3 gas particles to 2. And so most likely our delta S is going to be negative. Now also, if you recognize this as a combustion reaction, we have O2 and we're forming SO3, we'd say that's going to be exothermic, and so delta H should be negative. But if we want to make sure, we need to know the numbers. And so for delta H, we can do the products minus reactants thing. And we get, so products is the SO3, and it's minus 396. Remember, the 2 comes down. Minus reactants, so SO2, which is minus 297. Remember, oxygen, it's an element in its center state, and so its enthalpy of formation, Gibbs-free energy of formation are 0. And so we get a delta H of negative, which does correspond to an exothermic process. And so that means that the entropy of the surroundings should increase. And so we can also calculate our delta S. Notice for the delta S, we do have to include oxygen because, again, for entropy, you can actually determine in absolute terms. And so elements in their center state do not have 0 entropies, just the Gibbs-free energy and the enthalpies. And so again, products minus reactants. And so 2 times 257 minus 205 plus 2 times 248. That gives us minus 187. And again, it's negative, consistent with going from 3 gas particles to 2 gas particles. And so that means the entropy of the system decreases. Now for the universe, we got to think about the surroundings, entropy of the surroundings, or think about delta G equals delta H minus T delta S. And so we saw previously that entropy of surroundings is increasing. Here we're seeing that the entropy of the system is decreasing. And so the entropy of the universe will depend on temperature. And so if we use delta G equals delta H minus T delta S, we calculate our delta H as that. Now watch your units. So we have here delta S in terms of joules per Kelvin, but we have to convert it to kilojoules. And so we just move the decimal point over 3. We have it here. And so we get a delta G of minus 142. And so that means at 298 Kelvin, the reaction is spontaneous. Remember, delta G negative corresponds to a delta S of universe positive. Now we can also calculate delta G by doing the products minus reactants thing. And so minus 371 times 2 minus 300 times 2 gives us a minus 142. And so doing products minus reactants or doing delta G equals delta H minus T delta S gives us the same answer. The two are going to be consistent. And so we saw that delta H and delta S have the same sign, which means that the spontaneity of the reaction is going to depend on temperature. Now we can actually calculate the transition temperature for where the reaction goes from being spontaneous to non-spontaneous. We assume that delta H and delta S are temperature independent. At the transition temperature, delta G equals 0, so we set that to 0. Add T delta S to both sides and divide both sides by delta S. And so we get the transition temperature equals delta H over delta S. And so our delta H was minus 198. Our delta S will move the decimal over 3 to give us minus 0.187 kilojoules per mole Kelvin. And that would give us a temperature of 1059. Now again, remember that the spontaneity of the reaction depends on temperature. When delta H and delta S of the system have the same sign, you will only get a reasonable answer for this question if delta H and delta S have the same sign, because temperature always has to be positive because it is in units of Kelvin. And so above 1059, it's non-spontaneous. We could also call it reactant favor, meaning the reactants are more stable. At 1059, the reaction is reversible. Our delta G is equal to 0. At 298, we saw that it was spontaneous, meaning product favored, meaning the products are more stable. And the lower the temperature we go, the more product favored we get, the more spontaneous the reaction. And so please make sure you're able to use these equations. For enthalpy, entropy, Gibbs free energy, they're all state functions. And so we can always do the products minus reactants thing. Remember, we defined delta G as minus T delta S of the universe. We also have delta G equals delta H minus T delta S of the system. Please don't get confused between these two. It is a little confusing at that minus T delta S, but one is for the universe and one is for the system. And again, if delta H and delta S have the same sign, you can actually calculate the temperature at which the reaction is going from being spontaneous to non-spontaneous, assuming that delta H and delta S of the system are temperature independent. And so also please remember there's only 4 possibilities: always spontaneous, never spontaneous, spontaneous at high temperature, and spontaneous at low temperature. I hope that helps.